So for our review sheet, and this is to help us get ready for our quiz tomorrow, which I promise will be short, both because we're remote and also because I don't want to grade a long quiz. Anyway. All right, so we're given some position versus time data that looks parabolic. It's kind of nice because we can try to estimate where things go. The first thing is to give a description of the motion of this object. And I always like to do starts at 0 meters, tells us where we started. And then it moves in a positive direction. And it looks like if I use my slopometer to look at my velocity here, the velocity my velocity decreases because my slope gets flatter. So I don't know. You want to say something about it slows down or its velocity gets smaller or something. I'm going to say it slows down. Let's see. It's probably come to a stop up here. Well, I'll put that in my next line. Stops at, and I can say my distance, 50 meters, in 10 seconds. So you could almost draw that graph from that information. I know I start at 0. I know I end up at 50. It takes me 10 seconds to get there. And by the time I get there, I have a velocity of 0. Okay, so next, draw a motion map for the object, and it says it wants velocity and acceleration vectors. We could actually, if we wanted to be quantitative about this, we could actually figure out how to make these measurements match the measurements up here. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. I don't like that. I want there to be 10. 9, 10, 0, 1 meter. Sorry, 10 meters. No, 5 meters. 10 meters, 15 meters, 20 meters, 30 meters, 40. Whoops, how did I do that? 25, 30, 35, 40, 45. I'm just going to blame it on being Monday and a holiday week when I'm the only one who has to work. All right. So for my dots, I have one at 0 meters. My next one is at 10 meters. After that, it's just before 20. This looks like 25. A little bit past 30. A little bit before 40. These seem kind of weird down here. Past 35. Let's see, we got 125. Past 30. Just before 40. A little bit after 40. 45. Yeesh. So they're pretty close together. I'm going to go with that. And remember, guys, as long as I can see your trend through your motion map, it doesn't have to be perfect. These are just sketches about what we think is going on. And I'm going to copy these down here for acceleration. So the easiest one, I think, is always the velocity one, because all we're looking for the velocity one is drawing an arrow that's half the length of the distance between the dots. So I'm going to draw my arrows up here. For acceleration, what I want to look at is, I still feel like that one's in the wrong place. For acceleration, I want to look at how those arrows are changing and draw arrows in response to that. And so what it looks like is happening is that these arrows are getting shorter. So if they're getting shorter, it's like I'm adding the length of an arrow that's pointing in the opposite direction. And we know that our unit is about constant acceleration. So no matter what happens with these, they should always be similar lengths just because of what unit we're in. So even if you don't understand like how you get that from the velocity versus time motion map, that's the whole theme of the unit. You should all be the same, so they kind of overlap when you get to the end. There you go. If you guys did okay on that, I can't see any of you, so it's a little bit hard for me to get feedback from you guys. But let me know if you have questions or you want me to talk about something more in depth. So part C says determine the instantaneous velocity of the object at time equals 2 seconds and explain how you did it. So there's 2 seconds on our plot. We've talked about how to do instantaneous velocity. What you're going to want to do is determine the average velocity based on the data from 2 points that are an equal amount of time on either side. So it's finding the average velocity of two other points. If you want to use 1 and 3, which you certainly could, you would need to identify what values you think there were. So if you used 1 and 3 seconds to determine that, then your average velocity between those 2 points is going to be something like, this is 25 meters minus 10 meters divided by 3 seconds minus 1 second. So it's 2. So it's going to be 15 meters in 2 seconds. So I got 7.5 meters per second. So that's one way you could do it. You could also use the data points at 0 and 4 for that. So if you use 0 and 4 seconds, and either one works, and you don't have to do both. For average velocity, we need to estimate where we are here. I think I'm going to put us at 32. So 32 meters minus 0 meters divided by 4 seconds minus 0 seconds. So it's going to give us 32 meters over 4 seconds, which is 8 meters per second. So these are in the same ballpark. I want you guys to feel confident that as long as you show me your work, you should always show me all the numbers that you use in your calculation, because that helps me to figure out what you were thinking and what your reasoning was when you solved your problem. Don't worry about, one's 7.5 and one's 8. That's not exactly what I'm looking for here. I'm actually looking for the reasoning part. I want to see evidence that you knew to use 2 points that were on an equal time on either side of these, and that you understood that the average velocity between those 2 points was equal to the instantaneous velocity at 2. That's the thing that's the important part about this kind of question. It's not just the number at the end. So keep that in mind. And so when you do quiz for me, make sure that you show me what your reasoning was. Okay, for part D, it says, assume the initial velocity was 10 meters per second. Determine the acceleration of the object. So what that's telling us is that we've got a velocity here, 10 meters per second. And we have calculated a velocity for 2 seconds. So if I use my first one here, 7.5, then my acceleration is going to be my change in velocity divided by change in time. And my velocity here, my final velocity would be 7.5 meters per second minus my 10 meters per second that was given to me in the problem, divided by 2 seconds minus 0 seconds. So this one is saying, let's see, minus 2.5 meters per second divided by 2 seconds. It's going to be minus 1.25 meters per second squared. Sorry, you can't read my units there, but it's minus 1.25 meters per second squared for my acceleration. And that goes along with this one. It would be about minus 1 meter per second squared if I used my value from this blue one here from 8 meters per second. So again, this is just is the value that you used here to calculate your acceleration consistent with what you found above. So I'm worried about looking at your reasoning and your logic, and the number at the end might be a little bit different, and that's okay. So lastly, E says sketch a corresponding velocity time graph for the graph above. So we've been given a couple of pieces of information here. We've got that at 10 seconds we're at about 0, at 0 seconds we're about 10 meters per second. At 2 seconds we're at about 7.5 or 8. So if I take a look down here, 1, 2, 3, 4, 5, 0 seconds, 2 seconds, 4, 6, 8, 10. At 10, we're at 0. Dr. O'Malley needs to edit this graph. Okay, and we start there. We can just draw this as a straight line, to be honest. Get my straight edge here. So we should have something that looks like that. It's just a sketch, and it's just showing us how that velocity is changing with time. Does anybody have any questions about the first page? Anything you want to talk about? Okay, second page. Use the graph to answer the following questions. So first, if we want to describe the motion of the object, we can look at this and say, okay, this object is moving in the positive direction because it has a positive slope, and it's moving from, oh, sorry, hold on, that's not right. It has a negative velocity, so it's moving in the negative direction. But what it's telling us, because it's approaching 0, is that it's slowing down. So our object is in negative direction. And we know that because the velocity is negative. And we know that it is slowing down because the velocity is approaching 0. That's kind of a calculus way to say that. Means we're getting closer to having a velocity of 0, so our object must be slowing down. Next, it says determine the acceleration of the object from the graph. Yeah, no problem. We can do that because we can pull a couple of data points off of this. So if I use the start and the end of that line, I know that my acceleration is my change in velocity divided by my change in time, and that I have final velocity minus initial velocity. I'll just put change in time there. Remember, you guys are going to be given equations, so you won't have to memorize those. My final position here has a velocity of 0 meters per second, and I'm subtracting from that my minus 15 meters per second. And it looks like that happens at 5, 6, 7, 8 seconds. So if this is plus 15 meters per second, because it's minus minus, 8 seconds, it's going to be less of 2. So 15 divided by 8, 1.875 meters per second, or meters per second squared. There we go. Then it says shade the portion of the graph that represents the displacement of the object from 2 to 6 seconds. Well, that's nice. We don't have to actually calculate it. We just have to color it in. So I'm going to find 2 and 6 seconds. And we know that on a velocity versus time graph, the displacement is the area that's between the graph and the axis. And so I'm going to find 2 seconds. There's 2 and 6. Color it in. There we go. Calculate the velocity of the object at 2 seconds and at 6 seconds. No, you're not allowed to just take the values off the graph. Okay. So now we have to figure out what is our velocity here and what is our velocity here. All right, so things that we know. We know that our acceleration is 1.875 meters per second squared. We know that our initial velocity is minus 15 meters per second. We know our times for each of those are 2 and 6 seconds, and we need to solve for a final velocity. So if we know our acceleration is our final velocity minus an initial velocity divided by time, if we are using the 2 and 6 seconds as our final velocity and minus 15 as our initial, then we can solve for this guy right here. I'm just going to rewrite the equation because for me that's what makes it the easiest. So I'm going to multiply both sides by change in time. So acceleration times change in time equals final velocity minus initial velocity. If I want to isolate final velocity equals acceleration times change in time plus initial velocity. So I can use that to figure out what my velocities ought to be. Again, this is just an equation that we've used a whole bunch of times. We're just rearranging it so that we can use it to solve a problem. So for, I'm going to write this as velocity at 2 seconds is equal to 1.875 meters per second squared times 2 seconds. And this is plus minus 15 meters per second. So I do that in my calculator. 1.875 already there, times 2, minus 15. So for my velocity at 2 seconds, I have minus 11.25 meters per second. And if I look up here, does that seem reasonable? Yeah, because that's minus 10. So for that, I think it's 11.25 meters per second. Now I'm going to figure out what it is at 6 seconds. So my velocity at 6 seconds is 1.875 meters per second squared times 6 seconds plus negative 15 meters per second. So 1.875 times 6 minus 15 minus 3.75 meters per second for that next one. Does that seem right? Yeah, it's just within the 5 there. Okay, next, calculate the object's displacement. Okay, this problem is just walking me right through all these steps. I know that my displacement is going to be my average velocity times time. So my average velocity there, I can just take these two, add them together, 11.25 plus minus 3.75 divided by 2 times the amount of time there. So that's going to be 6 seconds minus 2 seconds. So my change in time is actually 4 seconds. When I add these together, minus 11.25 minus 3.75. So my total there is 15 divided by 2 is minus 7.5 meters per second times 4 seconds. It's going to be 30. Minus 30 meters. So 30 meters in the negative direction. And that's going to be the area underneath this. If you were doing it as an area problem, you would have to first find your average and multiply it times the time. Or let's see, 1/2. Well, you can't even do it. It's not a whole triangle. So this would be complicated to do, because what you would need to do is know the area of the trapezoid, which is a lot, which is the same math as this. Or you would have to extend the triangle all the way and then subtract from it this triangle. So I'm not going to do that right now unless you guys need me to. This is really going to be your best way to go. All right, and then we switch problems. This was number 2. Now we go number 3. A car initially at rest accelerates at a constant rate. Remember, I take this a little. Accelerates at a rate of 4 meters per second squared for 6 seconds. How fast will the car be traveling at 6 seconds? So it also says that it's at rest. And so if we have something that's at rest, sorry, I put 0. Our initial velocity is going to be 0 meters per second. I put a 0 there because sometimes you put like what the time was at that speed. So we know we started at 0. We know our change in time. This looks like this. So we're going to use this equation just like we did here for problem number 3. So our final velocity is going to be acceleration times the change in time. So our initial velocity, which was 0. Our acceleration here is 4 meters per second squared times 6 seconds plus 0 meters per second. So this is going to be 24 meters per second is our final velocity. Last one on the page, a tailback, initially running at a velocity of 5 meters per second. So our initial velocity becomes very tired and slows down at a uniform rate. So it's an acceleration if he's slowing down at 0.25 meters per second squared. So because he's slowing down, this is going to go against what his velocity was. So it's going to have a different sign. How fast will he be running after going an additional 10 meters? Okay. So where do we have our position? Yeah. Okay. So we might have to two-step this one. So we've used this equation. Oops, 1/2. I apologize. 1/2 AT squared, because we need to figure out how long this is happening so that we can use our acceleration with our velocity with the time to use this equation and figure it out. So here we've got 10 meters equals 1/2 times minus 0.25 meters per second squared times time squared, and we're going to solve for time squared. So to do that, we need to multiply both sides by 2. 20 meters equals minus 0.25 meters per second squared times time squared. And then we need to divide both sides by minus 0.25. So 20 divided by minus 0.25. I got minus 80. Uh-oh. Right? This is going to be an imaginary number. Can you have an imaginary number? I wonder if my signs are wrong somewhere. I feel like my signs have to be wrong somewhere. But I think the numbers are right. So I'm going to do the square root of 80. See what that tells us. Where's my square root button? There we go. Okay, so this tells us the time is going to be 8.9 seconds. That sounds right. So if our time is 8.9 seconds, I'm just going to put a question mark there because I'll have to think about that one. And we want to know what our final velocity is going to be based on that acceleration. We can use our equation that we got up here. Final velocity equals acceleration times time plus our initial velocity. Our acceleration here is minus 0.25 meters per second squared times time, which we got is 8.9 seconds, plus our initial velocity, which is 5 meters per second. So this is going to be minus 0.25 times 8.9 plus 5. I got 2.78 meters per second. It's a lot slower, but he's still moving. All right. What questions do you guys have about the second page? Any questions? All right. Draw a motion map for the ramp of motion of the ball when it's released from rest. So when it starts, it's going to have 0 velocity. It's going to speed up and then go flat. So this should look something like they're close together at the top. They spread out as it goes down. And then once you hit the ramp, it's a constant rate. So it should be something like that. For number 6, draw a motion map along the ramp for the motion of the ball when released from rest. So they're going to be close together up at the top. They're going to spread out as it goes down. Once it gets to the bottom, it's going to stay at about an equal rate. And then as it moves up, it's going to actually mirror what happened over here. So we're going to have close together up at the top of the hill. They get farther apart. Once it hits a flat area, it'll have a constant velocity because there's nothing there to slow it down or speed it up. And it slows down as it goes back uphill. I really like this one. So if you have questions about it, make sure you let me know. So we've got position and time graph. A says displacement from 0 to 3 seconds. You'll notice 3 seconds is kind of special because that's where they intersect each other. That means at that point they've both traveled exactly the same. They have the same displacement. So what I would say here is that A is equal to B. Displacement from 0 to 1.5 seconds is going to be halfway there. The one that gets furthest at that point is with the straight line, which is A. So A is going to be greater than B. Displacement from 1.5 to 3 seconds, the second part, which one had the biggest change? It's going to be B because it started from farther away, even though they ended up at the same place. So I like to write it that way. You could also write it B is greater than A. Those two things mean the same thing. The average velocity from 0 to 3 seconds. So remember, for average velocity, if you're looking at 0 and 3 seconds, it doesn't matter which one you look at, you're going to use the same data at the beginning as you look at the end. So these two are going to be the same. The average is going to be the same. For the average velocity from 0 to 1.5 is going to be halfway. A's covered more distance and has more displacement than B. So A is going to have a higher average velocity than B. The velocity from 1.5 to 3, for the same reason that B was greater displacement, it's going to be greater velocity because it traveled more distance in the same amount of time. So B is greater than A. The instantaneous velocity at 3 seconds, which one's faster? Well, I can use my slopometer and put it down on the paper and see which one has a steeper slope at 3 seconds. And the one that has a steeper slope there is B. So B is greater than A. The instantaneous velocity at 0 seconds, we can do the same way. Which one has a steeper slope? A has a steeper slope. So A is greater than B. So that says if the motion of B is uniformly accelerated, what time will both graphs have exactly the same slope? They should have the same slope at exactly 1.5 seconds because that's where the average velocity for A is going to be equal to the instantaneous velocity. Sorry, the average velocity for A is going to be equal to the average velocity at exactly that midpoint for B because they have those two data points in common. And that's the point where that you're right in the middle of those two data points. So that's going to be at 1.5 seconds. Okay, what questions do you guys have about this page? You guys have any questions about stacks of graphs? I'm probably not going to put stacks of graphs on the quiz. They're super fun, but they're kind of it's tricky for me to give you feedback if I can't write on your paper. All right, it's 9:30, guys. If you have any questions for me, feel free to stick around in the meet or send me an email or a remind, and I'd be happy to help you out. You're going to be given your equations tomorrow, so don't worry about memorizing those. Just focus on, making sure that you understand how to solve these problems. I'm going to shoot for like a front and back of one sheet of paper for the quiz tomorrow. It's past my time, so if you guys don't have any questions for me, you are free to go, and I will see you tomorrow.